All right. So the last thing that we left off with last time is we were discussing the notion of degree and order in polynomial and power series rings. And so let's rip off a couple of things from this. Yellow. So let me do this. Ring. So is R and R. Well, this is kind of the first application, if you will, of the degree and order. So let's do the RX case first. Suppose F and G are polynomials such that F G is equal to 0. If F and G are non-zero, so let's just suppose this, then degree of F and the degree of G are greater than or equal to 0. Therefore, degree of FG is greater than or equal to 0, which is the kind. Because the degree of the zero polynomial is undefined, negative infinity, whatever you like. And so instead of using the back end for polynomials for power series, you use the front end. Give you another tool. And this is actually, this is a simple observation, but it's very important. If R is a domain, then the units of the polynomial ring coincide with the units of R. So to be a unit polynomial, you have to be a unit, you have to be a constant unit. Notice this one sort of glaringly omits power series because the same result is not true there. Proof, suppose f of x is a unit in R power x, Rx polynomial ring. So there exists g of x in Rx with f of x, g of x equal to 1. Taking the degree of both sides, we get and of course, since these are non-negative, this forces be 0. Therefore, F is in R, and F is a unit in R from, of course, this equation right here. So in particular, any unit here is contained in here, and the other containment is pretty straightforward, isn't it? If you have a unit here, it has to be a unit polynomial. Okay, any questions so far? Notice a couple of remarks about this last proposition. Number one, I left out power series because the analogous result of power series is not true. You gotta massage it a little bit. We'll look at that in a moment. Also, you might ask yourself, what happens if R is not a domain, or if it's got zero divisors? Of course, the fact that we're talking about units implies that R is a ring with identity, right? But what if it's got zero divisors in it? What's the structure of URX? And it's not the same anymore, but it's a little bit more general. And you should, of course, whatever the answer to this happens to be, should collapse to this in the case that R is a domain. Okay. Yeah, I'll just finish this up this way. Proposition 228. Let R be a commutative ring with one, and I an ideal. So you have this ring, you have an ideal in it. So here are two important ideals associated with I in the polynomial. Then Ix, and I think this notation is suggestive. This just means, if you will, polynomials, all of whose coefficients are in I. And Ix, of course, we know this notation. This is the smallest idea, or the smallest ideal of Rx that contains both I and X. By the way, can we describe what this looks like though? There's kind of an easy description in the flavor of this one.
On the polynomial such that A0 is 9.
That's right. This is the set of polynomial such that A0 is in I and everybody else complete freedom are both ideals of Rx. Notice that, of course, this one is contained in this one, as a matter of fact. What is more, number one, Rx mod Ix is isomorphic to R mod Ix. And what do you suppose this one's isomorphic to? Good. So let me make an observation about this. Assuming you don't believe the theorem. Observe that I is prime. Well, what happens if I is prime? Then this is an integral domain, which means that that thing is prime as well. I is prime if and only if Ix in Rx prime if and only if, and of course, again, if I is prime, then this quotient structure is an integral domain, and an integral domain's polynomial ring is an integral domain. So I is prime if and only if Ix, I bracket X, I comma X are prime. Notice that I is maximal. If I is maximal, then that thing is field, which means that thing is field, which means that thing is maximal. Is converse true? So if you have a maximal ideal in Rx, is it of that form? The answer is, in a certain sense, almost never. This is actually an interesting case where power series actually, the answer is yes for power series. We'll see that in a moment. But the answer is sort of almost never here. Let me give you kind of a silly example, right? What if R itself is a field, right? And so what we're looking at here is, what a little R symbol. This is a polynomial ring over a field, okay? So what's the maximal ideal of a field? 0, right? So if you look at R not 0, right, that's a field, right? This means, so the analog of this in the case that R is a field is the ideal generated by X is the maximal ideal. And this is true if your coefficient ring is a field. So if you have Fx, then the ideal generated by X is maximal because when you mod out by it, you get the field, right? However, think about your favorite polynomial ring over a field. The ideal generated by X is a maximal ideal, but it ain't the only one, right? Just take, for example, Q. What else do you have? You have 1 plus X. You have 1 plus X squared, right? And there's just this whole slew of maximal ideals that are not of the form I comma X, right? So we don't get a good converse here. Polynomials, in a certain sense, power series are usually much more misbehaved than polynomial rings are. But this is an unusual case where they behave better. There's a couple of places where and it's because of the units thing that we'll talk about in a moment. But it turns out, if you have, you all remember what a quasi-local ring is, right? It's got a unique maximal ideal, right? If you look for a commutative ring with identity, if you have a quasi-local ring, its power series ring is also quasi-local. There's a one-to-one correspondence between the maximal ideals in the power series ring and the maximal ideals in the original ring. And so if it's quasi-local, the original ring, so is the other one, or even semi-quasi-local. However, polynomial rings never have this property, like never. Even if you have a field that only has a 0 ideal, you have infinitely many maximal ideals. Okay. So, any questions on that? Okay, so let me get rid of the suspense and we'll talk about power series as promised. All right. So there's some analog, there's a lot of results for power series that are analogous. So the first two theorems I've got in my notes I've already done yet. What do we know? If R is a domain, the ideal generated by X, anyway, clear, and the power series ring is prime, and R power X is a domain. This is exactly the analog for what happens with polynomials. Let me, take you to the place where this first diverges and actually in part makes power series for this aspect of things a little bit easier. Well, the units are harder, but the units have some consequences. Proposition. I think that's all. Yeah. Let R be a community thing with one, then the units of our power X are equal to the units of R, this X, Rx. Another way to put this is the set of f of x and R power x such that f of 0 is a unit. Yes.
Do we want X R of
Power x. Yes. So the unit power series, all you have to do is start with the unit. Let me point out. I'm not going to give you a formal proof. I'm going to give you something that I hope is better, that will impart some understanding, and I'll tell you how you go about it if you wanted to be a little bit more careful. Let's point out that this containment is certainly true, because if A0 plus A1x is in the unit power theory, then there exists B0 plus B1x plus such that A0 plus A1x plus times B0 plus B1x plus yada yada is equal to 1, which implies immediately that A0, B0, 1. Therefore, A0 is a unit in R, which is really, that's the only restriction on there, is the constant term is a unit. But why so big is the question. So this is, in a certain sense, this is the most naive thing that you must have a unit. And actually this very naive thing, all you gotta do is start a unit, that's all you need. Why does the other contain that whole? So I can simplify this a little bit. Let me point this out here. Suppose A0 plus A1, well, let me write it this way. U plus A1x plus A2x squared plus is notice that this is equal to U right? So certainly since that beginning term is a unit, I can pull out a factor of this unit like this. And the observation I want to make is that this is a unit if and only if the whole thing. Right, because I factored out a unit, so the whole shebang is a unit if and only if this piece. So this allows me to simplify. By showing any power series of form 1 plus a1x plus a2x squared is the unit. And that's really all we're gonna do. So. So we'll go back to high school just for a moment. Only I'll call this Hilbert's High School because
It's published in 2016, so.
well, did you say, oh, did you? Yeah, actually, that might work out well for them.
Reminded, hopefully.
So let's divide, shall we? Just like we were in high school, right? This is the magic of power series and the magic of starting with 1. Okay, let me see. How many times does 1 go into 1? Well, I can do that. So this is really sloppy and terrible. I can't believe I'm recording this for posterity. But what it will do is it will show us how we would do a real proof. It gives the idea, okay, this has got to be true, and it also shows how to prove it sort of more correctly. And subtract. Like this. Now to build the second term, what are we going to do? Minus a1 and x, right? And so now it gets a little bit yucky, right? Because we get minus a1 x, and we get minus a1 squared, x squared, minus a1, a2, x cubed, and so forth. And you subtract again. And so I get something like a1 squared minus a2, x squared, plus a1, a2 minus a3, x cubed. You continue this process, right? And so what's the burden? I mean, anybody can subtract. The burden is can you multiply this by something that gives you the leading term every time? And the answer is yes, because it's a 1. Or more generally, unit. So like the next term would be plus a1 squared minus a2 x squared. This will get you a bigger mess that'll subtract down to 0, and then you'll get another linear combination of products of these coefficients, but you can keep doing this forever, right? It's power series, so you never have to stop, right? This is why this works, right? So this will just keep going, and you build a power series that works. How would you do this more carefully? Well, inductively, what you would do is solve this system of equations, because that's really what you have to do, right? I mean, to more carefully, what you would do in our reduced case is 1x plus a2x squared plus a3x cubed forever and ever. Now you've got to find a solution. And so you immediately get b0 equals 1, right? And you get this, sequence of equations, you get, B1, well, let's see, I guess the burden's here. We'll say A1, B0 plus, B1 equals 0. You get, let's see, and for the quadratic term, you get, we'll start here, A2, B0 plus, A1, B1 plus B2 equals 0, and then we get A3, B0 plus A2, A1, B1 plus A1, B2 plus B3 equals 0. And the reason you can solve these is because these are all in your equations. And each one of these equations, at every step, you'll have the previous thing, right? So you got B0 here. And what do we get? We'll give an A1. Right, so B1 is A1 times this. B1 is minus A1 times this. B2, now you know B0, B1, and we know the rest of them, so we put this here and there's B2. So this gives you really set of equations for this fine inductively, right? And so if you really want to be careful, you'll assume that you've got the solution at the end step and then show you got it at the n plus 1 step. But that's essentially it, right? Intuitively speaking, the process never has to stop because it's a power series ring, and the fact that you can keep going is because this is a unit, right? Okay, any questions on that? So here's something that I can't resist sort of ripping off. This is something we've seen before, but it's nice to kind of come full circle and see. Corollary. I think, if F is a field, then every non-zero element of F power X is a form X to the N UX with N greater than or equal to 0 and UX in yeah, U F power X. So, and of course, what that means is this means that U of 0 is not 0. Right, because any power theory has got a non-zero constant term has to be a unit because my coefficient ring this time is a field. So, in particular, well, so if you take a non-zero element of this, just take the power series, factor out x to the n. You can always factor out x to the n out of any power series. I mean, n might be 0, but you can certainly factor it out. And what's left over is a unit. So in particular, F power X is a Noetherian valuation. Because any two non-zero elements look like this, whichever one has the smallest exponent of x divides the other one. So and of course it's Noetherian because it's, well, in fact, not only that, you might have seen earlier, probably in an earlier algebra course, that in fact F power X is Euclidean domain, as a matter of fact. And another way to see this is a Noetherian valuation domain also is synonymous with a principal ideal domain that has only one non-zero prime element, up to associates. Right. Let me give you another interesting consequence of this unit kind of business. Problems. Two through six. If, well, let's split RV domain. Just so, you can actually generalize this out of domains pretty easily, but I just want to make sure that I know what I'm talking about when I talk about irreducibles. If A in R is irreducible, then any power series of the form A plus X F of X is irreducible. Yeah. R power X. Okay, so in other words, what this theorem says is, just like, this is sort of analog to the unit thing. The power series unit thing says if you've got a constant, if you've got a power series whose constant term is a unit, the whole thing's a unit, right? This one says if you have a power series whose constant term is irreducible, it's irreducible. Proof. Suppose A plus X F of X can be written as, let's say, alpha 0 plus alpha 1 X forever, beta 0 plus beta 1 X plus forever. So suppose I factor it. This implies that A is equal to alpha 0, beta 0, just as a factorization of R. Well, what do we know about A? It's irreducible. As A is irreducible, we can say beta 0 is a unit in R without loss of generality, because one of these two has to be a unit. Therefore, beta 0 plus beta 1 X is a unit in R power X. So A plus X F of X is irreducible. So this is, well, so let's ask ourselves this, right? The unit theorem says if you have a power series whose constant term is a unit, then it's a unit. And also, if you have a power series that's a unit, its constant term has to be a unit. What about this? Is it that strong here? So what I have, the statement of this basically says if the constant term is irreducible, then the power series is irreducible. Does the other direction hold? That is to say, do all irreducible power series have to begin with Well, let me ask you this. This. Six plus X. It's certainly not, so if I replace the power X with polynomials, it's certainly reduced by, no way does that break down, because that's a degree one polynomial. Right, so.
Can we do the same like division trick?
Sort of, there's lots of choices to make. 6 plus X actually does factor. You do the rest. So, well, let's start doing a little bit of the rest. How can we fill in the blanks here? Right, so certainly that's 6, but I need to fill in, let's see, 2 times something, 3 times something equals 1. Can I do that?
Yeah.
Why can I do that? Why is there a linear combination of 2 and 3 that gives me 1?
That's what that.
They are coprime and Z is a principal ideal domain, right? So I can just find some solution. By the way, this will anger up the blood, but the solution's not unique, right? Somebody give me a solution. 3 times what? Okay, so we could do that be X, and this will be minus X. Does that look right? What about the next step? So now we've got to get a 0. Well, let's fill this in here. Alpha, beta. So what do we really have to do here? Well, you have to have 2 beta plus minus 1 plus 3 alpha equal to 0, right? Which is equivalent to 2 beta plus 3 alpha is equal to 1, right? So maybe alpha is, I don't know, 7, and that would be like, what, minus 10 or something like that? And then you go on to the cube, right? And same thing with alpha beta, but it boils down to, you'll make a mess with these middle terms, right? You'll make a mess of numbers. But the end game to this is, can I find an alpha and a beta such that 3 alpha plus 2 beta is equal to that mess of numbers? And the answer is yes, because they're coprime. So I can just go bananas here and factor this, right? So it looks like it might be true in the other direction, but it's not, unfortunately. But you can rip the theorem out of this one though, right? Because if you're coprime, if you've got coprime factors, you should be able to factor it down into power series that have the coprime factors in them, right? Again, in Z power X, so 6 plus X reduces in the power series. Notice all my examples are irreducible in the polynomial ring, but the power series grow big enough to allow 6 plus X to break apart, but 4 plus X actually is irreducible, even though 4 is not irreducible. Why is this the case? Well, if you can factor 4 plus x, I mean, you're actually kind of dead in the first step here. Notice there are a number of factorizations. 4, I picked 2 times 2, because that's the only chance that I would have of having a non-trivial factorization. If I go 4, 1, that's a unit, and I wasted my time. And, you know, you can assume that the negative signs are absorbed in the rest of the power series. You can just multiply that out. Notice that 4 is 2 times 2, 1 times 4. This is your only chance for a decomposition that's not trivial. But look what happens. At the linear term, you have 2b1 plus 2a1 equals 1. So it doesn't get down. Right. So we don't quite get, so this irreducible theorem is not quite as good in the unit theorem, and you don't get as strong converse, but nonetheless, it's still a fantastic theorem. Okay. I'm gonna sort of, this is the analog of the theorem that I just gave you for power series. So I'll kind of do this quick here. Proposition 2, 3, 8. Let R be commutative with identity and I and R an ideal. Commutative ring 1 and I and R an ideal. Then power x, and this is, I think, what you might think of it as alpha I x I. And Ix, which is equal to the f of x in Rx, so, or power x, such that f of 0 is a 9, are ideals of R power x. These are also important analogs of I in R power x. And number 1, R power x modulo I power x is isomorphic to R mod I power x. And 2, R power x modulo I x is isomorphic to R mod I. And we also have, just as we had before, I prime, if and only if I power x prime, if and only if I x. And again, as before, if I is maximal, then I comma x is maximal, just like we had with polynomials. But we are going to see a couple of subtle differences here. Let me, I didn't prove the analog result polynomial rings. So I'm just going to do, part 1 of this power series thing. And the proof of polynomials is essentially exactly the same. And I'll leave the parts 2 for polynomial power series to you. Because once you do, this was really, I think, the one that's just a little bit more difficult, although neither one of them hard. By the way, so this is a philosophical question, I guess. How would you prove this?
First isomorphism.
A true disciple. Yes, first isomorphism. There you go. I think there's I'll put in quotes, obvious homomorphism from here to here. This goes to just, yeah, the reduction plus R1 plus X plus R2 plus squared. Like that. I will let you verify that this is a homomorphism. It's not difficult to do. It's also, it's pretty clearly onto, isn't it? Right? Because no matter what choices of cosets, there's clearly just pull it back to, in fact, there's a lot of choices, aren't there? Right? Given an arbitrary coset, you've probably got a whole bunch of choices here. Objective. Homomorphism. And so notice that the kernel of this kernel of phi is the set of f of x such that f of x is 0, which is the set of f of x such that use notation here. 0 alpha k such that alpha k is in I. Well, k. So what does it mean to be in a kernel? It means that it has to go to 0, and the way it has to go to 0 is every one of these RIs has to be an I. So this is I power x by definition. So by first isomorphism theorem, R power x, my kernel phi is isomorphic to R mod I, the image, which of course subjectives to all of this, which is kernel phi is I power x. Okay. Any questions on that? Let me leave you with a theorem to think about. And this is, as I pointed out this earlier, this is drastically different than what happens in the polynomial case. Polynomials, you've always got infinitely many maximal ideals. Let R be a commutative ring with identity. Let R be a commutative ring with identity. Then there exists a one-to-one correspondence between the maximal ideals of R and maximal ideals of R power x given by these are the maximal ideals in R. That gives you a maximal ideal in X. You can check by our previous proposition that this is maximal ideal by looking at quotients. But the interesting thing is all maximal ideals R power X are this form. This is not true for polynomials. We'll discuss this Next time, any questions?